Hello viewers, welcome to this next session on carboxylic acids. In our previous session, we discussed about the structure, nomenclature and methods for the preparation of carboxylic acids. Our today's session has been planned that first we will review what we discussed in our previous session, then we will take up their properties, physical properties, then chemical properties, and amongst the chemical properties, today mainly we will take up the acidic nature of carboxylic acids. We will compare the acidic nature of carboxylic acid with other functional groups which we have studied earlier, alcohols and phenols. They also show acidic character. Then we will discuss that how do different substituents which are present in a molecule, they affect the acidic strength. They may be in aliphatic acids and aromatic acids. We will come across another briefly a topic which is called ortho effect, and then we will talk about the acidity of dicarboxylic acids. Finally, we will summarize what we have discussed today. Now, previously in our previous session we discussed that carboxylic acids are organic compounds which contain a functional group called carboxyl group, which is COOH. These compounds contain this functional group C double bond O OH. Here are few examples: methanoic acid commonly called formic acid, ethanoic acid commonly called acetic acid, or propanoic acid commonly called propionic acid. We had discussed the IUPAC nomenclature as well as the common nomenclature for these acids in our previous session. We also discussed their methods of preparation, and we found that many carboxylic acids they occur in nature, but others are synthesized generally by the oxidation of many other functional groups like primary alcohols or aldehydes or ketones. The acids can also be obtained by the hydrolysis of cyanides or by the carbonation of Grignard reagent. This is all we had discussed in our previous session. Now, today we continue with the properties. Let us first take up the physical properties of carboxylic acids. You know that any substance will show the properties whether physical or chemical mainly due to the functional group. In carboxylic acids, they exhibit dipole-dipole interactions because they have the polar CO bond and OH bond. They also exhibit intermolecular hydrogen bonding because hydrogen is attached to more electronegative oxygen in them. And due to this intermolecular hydrogen bonding, carboxylic acids they also exist as dimers. This way we can show that two acetic acid molecules they are forming a dimer. The carbonyl of one acid forms the hydrogen bond with the OH hydrogen of the other carboxylic acid, and carbonyl of this forms the hydrogen bond with the hydrogen of this acetic acid. So, it is not only acetic acids, other acids also they existed dimers wherever it is possible. Then amongst the physical properties, let us briefly take up their state. The lower aliphatic acids up to 9 carbon atoms are liquids like acetic acid, formic acid, they are all liquids, whereas the higher member are colorless waxy solids. These higher members are mostly called fatty acids, they are generally obtained from oils and fats. Then aromatic acid, benzoic acid and most of its derivatives they are colorless and light yellow solids. Odor, the lower aliphatic acids again like methanoic acid, ethanoic acid they possess sharp irritating odor. You are familiar with the odor of acetic acid, that is vinegar that you use. Then the odors of butanoic acid, pentanoic acid, hexanoic acid are also unpleasant. The higher acids have very little odor because they are not volatile enough. Then we talk about the solubility. The aliphatic acids up to butanoic acid, that is acids containing up to 4 carbons are miscible in water in all proportions. The solubility of these acids decreases as the molecular mass of the acids increases. This table shows the solubility. These are the 4 acids we find where infinity is written, they are miscible with water in all proportions, but as the size increases, the molecular mass increases, their solubility decreases. The reason for the decrease in solubility is due to increase in the carbon chain, which is a hydrophobic end, because the solubility is mainly due to the formation of hydrogen bonds between this carboxyl group and water molecules. As we find in this picture that this is the carboxyl group of the acid and it is forming hydrogen bonds with water molecules. So, as this end, that is this carbon chain, increases, then it is a water repellent, only hydrogen bonds can be formed on this end and solubility decreases. Then we talk about melting point. There is no fixed trend in the melting point of carboxylic acids, but one trend has been observed that the acid with even number of carbon atoms, they have higher melting point than the preceding acid with the odd number of carbon atoms. As we see in this table that acetic acid has a higher melting point than formic acid. Similarly, butanoic acid has a higher melting point than propanoic acid, although they have a lower melting point than acetic acid itself. But this type of trend is found, no fixed trend is there in the melting point of series of carboxylic acids. In boiling points, the carboxylic acids have higher boiling points than alcohols of the similar size due to high polarity, and also they are forming intermolecular hydrogen bonding also. The hydrogen bonds are also formed in alcohols, but the strength of the hydrogen bond formed in carboxylic acids is more. For example, the ethanoic acid boils at 118 degrees Celsius, while the alcohol of a compare molecular mass, it boils at 92.7 degrees Celsius. So, we can find here that there is a constant increase in the boiling point of carboxylic acids as the molecular mass is increasing. Now, we move on to chemical properties of carboxylic acids. You see, this is a basic structure for any carboxylic acid. This is functional group C double bond O OH. Now, the properties of carboxylic acids can be studied at different level. It may involve the cleavage of this OH bond, that is reaction may be due to cleavage of this OH bond, and whenever OH bond will cleave, oxygen is more electronegative, so hydrogen will be lost as H plus. So, the reactions are covered under acidic character of carboxylic acids. Then cleavage of CO bond, this CO single bond can also be cleaved, and in these reactions this hydroxyl group is substituted by some other groups. Then reactions due to C double bond O. You see, wherever we find this C double bond O, as in aldehydes or ketones, the reactions shown by those compounds are nucleophilic addition reactions, because oxygen being more electronegative, carbon acquires delta positive charge and nucleophile can attack here and pi bond breaks and addition may occur. But in carboxylic acids we do not find nucleophilic addition reactions, because once a nucleophile adds on to here, the nucleophiles are also electron rich and this hydroxyl is also electron rich, means they are electron withdrawing and they make the products little less stable. So, generally addition reactions of nucleophile are not shown by carboxylic acids, although they undergo addition of hydrogen, which we cover under the reduction of carboxylic acids. Then there are certain other reactions which are shown by the carboxyl group as a whole, like decarboxylation. And finally, the set of reactions which are shown by this side chain, it may be alkyl or aryl, where some substitution reactions generally occur. So, we can study the chemical properties of carboxylic acids under these 5 different headings. Let us first take up the reactions due to cleavage of this OH bond. As I said that cleavage of OH bond leads to acidic character of carboxylic acid. So, in aqueous medium, carboxylic acids turn blue litmus red, that is showing the acidic nature. This cleavage of this OH bond leads to the formation of carboxylate ion, and in aqueous medium this remains in equilibrium, that is water takes up the H plus ion forming H3O plus ion, and this H3O plus ion obviously acting as acid turns blue litmus red. Then if they are behaving as acids, they react with many metals like sodium or potassium. Carboxylic acids, when they react with active metals like sodium or potassium, they form their corresponding sodium salts. These are called sodium carboxylates, and hydrogen gas is liberated. Since they are acids, they will also react with bases. A common reaction with the base can be shown that base will abstract a hydrogen and we will get a carboxylate anion again. Like it is sodium hydroxide, when it reacts with carboxylic acids, we will get sodium salt of the carboxylic acid, that is sodium carboxylate, and water is formed in this. Carboxylic acids, they react with weaker bases like sodium carbonate also, forming sodium salt, and carbon dioxide is liberated. Sodium bicarbonate, here also carbon dioxide liberated and sodium salt is formed. They even react with ammonia, forming the ammonium salts. You have studied other functional group like alcohols or phenols before, and they are also known to show acidic behavior. Phenols can react with metals as well as strong bases like sodium hydroxide, but they do not react with these weak bases. Whereas alcohols, they react only with metals like sodium or potassium, and they do not react even with sodium hydroxide. It means they show different acidic nature, or they show different strength in their acidic behavior. Whenever we wish to compare the acidity of any functional group or any compound, we discuss about its acid dissociation constant. Let us say any substance HA is behaving as acid. It will dissociate into A minus and H plus. Obviously, we have eliminated here water because the dissociation will occur in presence of water. And we write the acid dissociation constant as concentration of the anionic part, concentration of this H plus ion divided by the concentration of undissociated acid. Now, more is the concentration of H plus ion, means stronger is the acid, and more concentration means the equilibrium is more towards right side. So, higher the value of Ka we will get, because if the concentration of this anion or H plus ion is more, means we can compare the acid strength of any substance by compare their Ka values. Higher the Ka values, stronger is the acid. But generally it becomes difficult to compare using the Ka values, because the Ka values are always with certain powers of 10, with some 10 raised to the power minus 5 or 10 raised to the minus 10, because these organic acids are not very strong acids. So, we generally use another term for this, that is pKa. pKa is minus log of Ka values. If Ka value is some factor multiplied by 10 raised to the power some power and minus again, so what will happen when we will take the minus log of that Ka, we will get a figure in positive terms, in positive numerals. But we will have to keep in mind that for higher value of Ka, we will get lower value of pKa. So, we can compare the acid strength of different substances by writing their pKa values. Lower the pKa value, stronger is the acid. And throughout our discussion, we will be using pKa values for different acids. Such as this ethanol, we have taken as example of alcohol. It dissociates to give ethoxide ion, where oxygen has the negative charge, and this ethyl group is further electron releasing. So, it means it is not stabilizing this anion. When we compare it with the phenol, after dissociation of phenol, we get a phenoxide ion, and this phenoxide anion is stabilized by resonance. This pair of electron moving here and this pi bond moves to this position, and we get different resonating structures. So, the negative charge on the oxygen in anion that is obtained from phenol is stabilized due to this resonance or distribution of negative charge over the ring. We have carboxylic acids. They ionize to give carboxylate anion. In carboxylate anion, this negative charge is again resonance stabilized, although there are only two resonating structures, but negative charge is distributed over two more electronegative oxygens. So, resonance stabilization of the carboxylate anion is more in comparison to that of phenoxide ion, because in phenoxide the negative charge is distributed to the carbon of the ring. So, this leads to the more stability or higher stability of carboxylate anion as compared to phenoxide ion, and phenoxide ion is more stable to ethoxide ion, and this order gives to the order of acidity of these three functional groups. We find that pK value for acetic acid is 4.8, that of phenol is 10, and that for alcohol is 16. So, alcohols are weakest acid amongst these, that is why they are able to react only with metals and they do not react with bases like sodium hydroxide or sodium carbonate, etc. Phenols are little more stronger acids than alcohols, and they are able to react with metals as well as with stronger bases like NaOH or COOH, but they are not strong enough to react with weaker bases like sodium carbonate or sodium bicarbonate. Whereas carboxylic acids, they react with all of these compounds, that is sodium carbonate, bicarbonate, and even ammonia also, that we have discussed before. The reaction of carboxylic acids with sodium bicarbonate is also used as a test for this functional group, because carbon dioxide is liberated in this and no other functional group liberates carbon dioxide on reaction with sodium bicarbonate. So, this becomes very specific for carboxylic acid and it is used as a test for this functional group. Next, let us take the effect of substituent on acidity of carboxylic acid. We use the same concept as we used in general for using HA before. This is any carboxylic acid. When dissolved in water, an equilibrium is set up, it dissociates to give carboxylate anion and H3O plus. We write the equilibrium constant, carboxylate anion and H3O plus, their concentration divided by the concentration of carboxylic acid and water. We write Ka, in which we take this concentration of water as constant and multiply by this K. We get this equilibrium constant Ka called acid dissociation constant, where we have these factors. Now, more the equilibrium will shift towards the right, more will be the concentration of carboxylate anion and H3O plus ion, which come here. So, we will have higher value for Ka, because concentration for undissociated acid in such a case will be less. So, again the same thing, higher the value of Ka, stronger is the acid, but as I said, we will be using pK value. So, for higher Ka we get the lower value of pK, and carboxylic acids with lower pK value are stronger acids. Now, on what factors this pK value will depend? Mainly it will be decided by the inductive effect. Let us take this carboxylate anion. This negative charge is resonance stabilized over these two oxygens. Now, what is the influence of this R group? If it is electron releasing, it means destabilizing the carboxylate anion, and if it is electron withdrawing, means it is stabilizing the carboxylate anion. So, if the carboxylate anion is stabilized, it means the acid from which it is obtained will be a stronger acid, and if it is destabilized, means acid from which it is obtained is a weaker acid. Let us compare the acidity of formic acid, acetic acid, then this is propanoic acid and benzoic acid. If we take at a level formic acid and we say that this H is replaced by some electron withdrawing or electron releasing groups. Say in acetic acid, this hydrogen is replaced by methyl, which is electron releasing. So, obviously, this will be destabilizing the corresponding anion, means acetic acid should be a weaker acid than formic, and we find it to be so, that acetic acid is a weaker acid than formic acid. Let us compare with benzoic acid. We see the benzene ring which is attached to this carboxylic group, it produces its electron withdrawing influence by the inductive effect, whereas it comes in resonance also with it, and due to resonance it is electron releasing. And similarly, this alkene group also is electron releasing due to resonance, electron withdrawing due to inductive effect. Inductive effect is caused by this carbon which is sp2 hybridized here. Now, we can show this resonance like this, that this is the resonance of the ring. This is the resonance of the carboxyl group, carboxylate anion. Like the p orbitals are perpendicular to on this carbon as well as on this oxygen. They are in a plane which is perpendicular to plane of this portion of the molecule. And now what happens? This p orbital of this carbon overlaps with the p orbital of this benzene ring carbon also. So, we can show this electron distribution, that here is a conjugation of the ring. These are the electrons on carboxylate anion, and now there is an extended conjugation, that is they mix up here and there is extended conjugation of ring pi electrons as well as carboxylate anion electrons. So, benzene ring is causing both the effects. As I said, by inductive effect it is electron withdrawing, and had it been the only effect, benzoic acid should have been a stronger acid than formic acid, but it is weaker because it is electron releasing also due to resonance effect, and it has its pKa value 4.2. So, it is a stronger acid than acetic, but it is a weaker acid than formic acid. Now, let us take up the effect of other substance, like if a chlorine is present. Say this is chloroacetic acid. When a chlorine is present, it is electron withdrawing. So, overall this group now withdraws the electron and the pK value comes out to be 2.8. It is a stronger acid than acetic acid. And if it has a 3 methyl groups substituted on acetic acid, we call it as 2,2-dimethyl propanoic acid. Now, all these methyl groups are electron releasing. So, electron releasing inductive effect is increased, and here we find the pK value is 5.1. So, this is a weaker acid than acetic acid. If these electron withdrawing groups are more than 1, obviously they will have their additive effect. Acetic acid, 1 chloro group is introduced, pK is 2.8, 2 chlorines are introduced, pK becomes 1.3, 3 chlorines are introduced, that is trichloroacetic acid is a very strong acid with a pK value of 0.9. Again, the inductive effect works through the sigma bond, and the effect falls off dramatically when the distance increases. Like we have this acid where this chlorine is present at carbon number 2, in this carbon number 3, in this at carbon number 4, and here it is no halogen. It is a butanoic acid. We have 2 chlorobutanoic, 3 chlorobutanoic and 4 chlorobutanoic acids. What we find? The pK for butanoic acid is 4.9. When chlorine is very near to the carboxyl, pK is 2.8, that is stronger acid. When it is 2 bonds away, 3 chlorobutanoic acid, value comes out to be 4.1, and when it is a 4 bond away from it, value goes out to be 4.5. So, acid strength decreases when the electron withdrawing group moves away from the carboxyl group, because its electron withdrawing influence decreases. So, acid strength decreases when the electron withdrawing group moves away from the carboxyl group, because its electron withdrawing influence decreases. Next, let us see the effect of a particular group with different electronegativities. Say if I take different haloacids, this is haloacetic acid where different halogens are at this position, they have different electronegativities. Let us see how do they affect the acidity. When this halogen is fluorine, which has the maximum electronegativity, means maximum electron withdrawing influence, it shows a pK of 2.6. When it is substituted by chlorine, the pK is 2.8. When it is bromine, it is 2.9, and when it is iodine, it is 3.2. We find that iodine has got the minimum electronegativity amongst these halogens. So, iodoacetic acid is the weakest acid among these acids. Next, we take up the effect of substituent on the acidity of aromatic carboxylic acids. In aromatic carboxylic acids, if a group is present on this benzene ring which is electron releasing, then what it will be doing? It will increase the electron density here, and this ring now will not be able to withdraw electrons as strongly as simple benzene was doing. So, net result will be pKa will be more than 4.2, because simple benzoic acid has pKa of 4.2. And if this group is electron withdrawing, obviously now the ring will be able to withdraw electrons more strongly, it will be a stronger acid and pKa will be less than 4.2. Let us see the pKa values of different substituted aromatic acids. When this is a methyl group present, means I am talking about the tolvic acid, then methyl group can be present at the ortho position, at meta position or para position to it, but it is electron withdrawing by its inductive effect. So, we have these three situations, there is the ortho position, meta position and para position. You see, when methyl is substituted at meta or para position, the pKa values are more than 4.2, but at the ortho position where we expect maximum inductive effect to operate, the value is less than 4.2, means ortho methyl benzoic acid is a stronger acid than simple benzoic acid. We will come to the reason little later. Let us take up now chlorine. Chlorine is in a strong electron withdrawing group by inductive effect. So, obviously, it will increase the acidity, and we find that for all the three positions ortho, meta or para, it is a stronger acid than benzoic acid, and as the distance of the chlorine is increasing from this carboxyl group, the pKa value is increasing, means acidity is decreasing. Next we take up when it is a methoxyl group. Methoxyl group is electron withdrawing by inductive effect, but electron releasing by a resonance effect, and a resonance effect can operate through ortho and para position. You know that through meta position a resonance effect does not operate. So, what we find that meta-methoxy benzoic acid is slightly more acidic than simple benzoic acid. Ortho-methoxy is also stronger than simple benzoic acid, although here a resonance effect will be decreasing the acidity. And when this methoxyl at para position, inductive effect is very less and resonance effect is operative. So, this becomes less acidic than simple benzoic acid with a pKa value of 4.5. Nitro. Nitro is a strong electron withdrawing group by a resonance effect as well as by inductive effect, and we find that it may be present at any of these positions. The acids are stronger than simple benzoic acid. Now, one thing that we observe here, that ortho substituted benzoic acid, they are always stronger acids than simple benzoic acid, irrespective of the nature of the group, whether it is electron releasing or electron withdrawing. We call this effect as ortho effect. I will repeat here that what is observed in this ortho effect, it is observed that an ortho substituted benzoic acid is more acidic than the meta or para substitute isomer, and this effect does not depend on the nature of the substituent, whether it is electron donating or electron withdrawing. This was one observation which required explanation. The reason for this is that steric hindrance between the substituent and the neighboring carboxylate anion forces the carboxylate to bend out of the plane of the aromatic ring, and this conformational shift alters the delocalization of the charge. Means what happens in this figure, you see for benzoic acid that this is a carbon-carbon single bond, and I shown before that these p orbitals on these carbons, they are resonance stabilized and they come in resonance with the pi electron or the resonance of this carboxylate anion part also, and it comes in the same plane. But now what happens if there is a bulky group here in the ortho position in place of hydrogen here or here, then this carboxylate anion or carboxyl group does not remain in the same plane. Like suppose this is the plane of benzene ring and suppose this is the carboxylate anion. When there is a substituent at the ortho position, this bends like this and it comes in a plane which is perpendicular to the plane of the benzene ring as shown here. And now the resonance of the ring electrons and a resonance of the carboxylate anion does not exist. That is why it is shown here as a double bond, and here we have shown the dotted line. And when this resonance is not possible, the electron releasing effect of the benzene ring due to resonance is reduced. Now only inductive effect is operative, and that causes the increase in the acidity of these orthosubstituted benzoic acids. Let us take up the acidity of dicarboxylic acids. Dicarboxylic acids are those which have two carboxyl group in them, and we have to measure now two different dissociation constants are two pKa values, one for the first dissociation and second for the second dissociation. One carboxylate anion is formed by the dissociation of one carboxyl group, and we measure it as a pKa 1, and then when the second dissociation occurs we measure it as a pKa 2. pKa 2 value for any dicarboxylic acid will always be less than its first dissociation constant, that is pKa 1. Why? Because in first case the hydrogen is being lost from a neutral molecule, whereas for the second dissociation this H plus ion is to be lost from a negative ion. So, that becomes a difficult process. Let us see these pK 1 and pK 2 values for different acids. We have oxalic acid, malonic acid, succinic acid, glutaric acid, adipic acid and pymalic acid with N is equal to 1, 2, 3, 4, 5. This N represents the number of intervening carbon atoms here. In oxalic acid it is 0, the two carboxylic groups are just attached to each other, and then with one CH2, 2 CH2 and so on. And what we find? We find that as the intervening number of carbon atoms increases, the pKa is also increasing, and when we are reaching very close to this N is equal to 5, this value is very close to acetic acid. It means in beginning this carboxylic group is affecting the dissociation of another carboxyl group, because it acts as an electron withdrawing group towards the other carboxyl group and lowers its pKa, and this effect decreases with the increasing separation. So, low dicarboxylic acids are stronger acids for their first dissociation constant, and second dissociation constant obviously as I told you will be higher than the corresponding first dissociation. Let us take up example of this phthalic acid. In phthalic acid the two carboxyl groups are ortho to each other. Its pKa 1 is 2.89, pKa 2 is 5.51. Here it is a terephthalic acid. We find that its pKa 1 is 3.5, means pKa 1 value of two differently substituted dicarboxylic acids is different. Here it is easier, means this is acting as a stronger acid. The reason being that after the loss of one H plus ion, the remaining carboxylate anion is being stabilized by the hydrogen bond also, and we find that the second dissociation constant for terephthalic acid is higher, means pKa is lower for this, it is acting as a stronger acid, whereas for this it is acting as a weaker acid, because now the hydrogen of this carboxyl and the anion which is formed is attached by hydrogen bond, and it becomes difficult to lose the second hydrogen. So, that is why it is behaving as a weaker acid for its second dissociation. Next we take up a dicarboxylic acid which is unsaturated. This is its cis isomer malic acid, trans isomer fumaric acid. Here also we find the same thing, that first dissociation constant for this cis isomer is higher, means it is acting as a strong acid, pKa is lower in comparison to trans acid, because after dissociation the anion which is formed is stabilized by the hydrogen bond, but its second dissociation constant is lower, its pKa is higher, because now this hydrogen is now attached through hydrogen bond and becomes difficult to lose it. So, this was about the properties of carboxylic acid we discussed today. Mainly we discussed the dissociation of OH bond which leads to the acidic character. Today we discussed physical properties of carboxylic acid, then chemical properties of carboxylic acid, and then acidic nature of carboxylic acid. We compare the acidic strength of alcohol, phenol and carboxylic acids. Then we discussed the effect of substituent on the acid strength of aliphatic as well as aromatic carboxylic acids. We discussed the ortho effect, and then we took up the acidity of dicarboxylic acids. In our next session, we will take up other chemical properties of carboxylic acids which are due to carbonyl group or carboxyl group as a whole. Thank you.